right. Okay, great. So yeah, coming to the last session of today's tutorial, we wanted to be this a bit more interactive or a bit more hands-on than so far, because like Daniel already introduced, we want you to kind of get familiar with our code base, as we're kind of aiming to use this as a publicly available benchmark to kind of unify current approaches to the controlling the MOD network optimization problem. And yeah, I'm not sure if people have access to the website, because I already put the GitHub repository link there, but otherwise it is a quite short link. If you want to have a look at the repository yourself, you can basically just copy the link up there. It's on the Stanford ASL GitHub page, and the repository is called RL for AMOD. And before we go into actually how you can interact with this code base, I want to give you basically a brief overview on how we structured the code base, because we wanted to make it as unifiable as possible, so you can easily kind of add your own methods, for example, or add your own scenarios, to make basically the research more comparable across different works. And yeah, as Luigi already kind of introduced, here we have a different set of simulators available on different levels of fidelity, microscopic and macroscopic. We included all of our calibrated scenarios, all of our calibrated parameters for the scenarios, and also all of the calibrated parameters for the learning-based methods. So basically, this repository is ready to go. And to give you a brief overview about the contents, the most important files are actually one up here, which is a testing file and a training file. We set up in a way that the testing file is basically the main file where you can test your approaches. If it's, yes, zoom in, sorry, yes, I didn't, I guess, did it zoom? Yeah. Yeah, but we basically set it up in the way that here we have the testing file, which is able to test all types of different policies. If we're looking for learning-based ones, non-learning-based ones, MPC policies, basically everything goes through just one file. And then, of course, for our learning-based approaches, we also have a training file to train the reinforcement learning agents. Then in terms of further structure, then of course we have all of our algorithms saved in a specific folder, the implementations for our reinforcement learning agents, soft edge critic and actor critic, and then many further kind of baseline controllers that Luigi also just presented, like, for example, the eco-distribution controller. And here is basically where people could start adding their own methods. And yeah, if interested, we have this registry file where basically new models have to be registered, but this also provides an overview of all the models that we already put into the repository to basically test on the environments. Then of course we have the implementations of the our GNN networks for the actor and the critic networks of the reinforcement learning agents, and then all of the files concerning the simulations. So one is the macroscopic simulations that we were presenting results, for example, in my presentation, and then we have this Sumo more simulation with a higher fidelity, which were the results that Luigi was just presenting. Yeah, to kind of make it easier to start interacting with this repository, we made a tutorial Jupyter notebook. That, of course, if you say, well, now it's 5 p.m., I just want to kind of scroll through it, you're more than happy to just scroll through it. But if anybody wants to be more interacting with it, we also set it up so it kind of works seamlessly with Google Colab. So you can be able to open up this tutorial notebook in Google Colab and kind of start interacting with our code base directly. Yeah, I'm not sure if there's reload again, sorry. Well, I will basically kind of do it live. If you want, you can follow along, or you can basically just watch me do it and watch to give you like an overview and how our code base works. If the Wi-Fi is on my side of the when I thought there would be maybe problems in the tutorial, I didn't think the internet would be already the first, the first challenge of the day. Well, I just tested it like 10 minutes ago. I don't know why now it's. It just needed a bit of time. Okay, well, we can basically directly clone. I opened this tutorial file within Google Colab, like so, by using the GitHub link that we provided. Okay, I feel like the internet is kind of. Well, if this is not working, I can also just maybe show you the already set tutorial. I'm not sure if this is basically just an area where to write the connection, but. Yeah, it's well, but I was literally testing like 10 minutes ago without any issues.
If you reconnect.
Yeah. Also, get out. Yeah, your internet connection is unstable. Thank you. Well, I mean, worst case, I will show it to you in a less interactive manner, I guess. Because I think if it's not working for me, it probably won't be working for other people. Okay. Well, I guess for now I can give you the introduction basically without Google Colab. And then of course hopefully when you try this you have a better internet connection and you can actually interact with the tutorial. But yeah, it's basically self-contained, so it's in a way to directly run. Okay, now it's loading. Yeah, I'm not sure if it's on my side or if it's just the Wi-Fi in general.
Yeah, maybe to understand how interactive we want to make it. Do you plan on doing this now or so maybe the interactive part is.
Okay, then yeah, I guess we give up on the internet connection, but it's fine like that. As I said, because the notebook is self-contained, so basically at home you can directly run it in Google Colab the way I just showed. If it would work, you could just open it up in Google Colab. And I already put in everything that you need to do to install the packages and to clone the packages. So basically all of the cells should run immediately opening up in Google Colab. And yeah, since it's a bit annoying to install Sumo, obviously in Google Colab in this tutorial, we're talking about the macro environment, well, the macroscopic environment, and where, like Gigi presented, we have different already calibrated scenarios from different cities, like New York City, San Francisco, Washington, D.C., and Shenzhen. And in this notebook, we're actually looking at the New York City Brooklyn scenario, which is specifically interesting because if you here look at the demand distribution over the different regions over time, you can see that the demand is very heavily imbalancedly distributed. So an effective rebalancing strategy can actually have a very big impact in the scenario. So it's very nice, of course, for us to evaluate the different rebalancing strategies. And yeah, so in our repository, we of course provide a wide set of baseline policies that we aim to use so people can benchmark their policies and compare them to the performance. And of course, the overall goal is to always outperform the no control policy, right? So you would always try to find a policy that is better than just doing nothing in the current environment. And so we start out by just running a random policy in the environment to see how it's doing. And like I said, basically everything you need to have is this testing file, which you basically can import like this, or if you want to just run it from the command line, you would just run the testing file directly. And we already provide a set of default parameters, but you can override all of the parameters basically according to what you want to test. First, you can always choose the simulator name, of course, which is either macro for the macroscopic environment, or you just change it into Sumo to directly seemingly change to the Sumo environment. Then here in the model name, you basically just specify the model that you want to test. Here it's the kind of very simple random rebalancing policy, but you can change it out with a more complex controller, as you see later on, or even also the learning-based methods. Then you can choose, of course, the city as the scenario that you want to run on. And our repository usually runs with Cplex, but we change it in a way that if you're not having access to a Cplex simulation, and you just don't provide a Cplex path, we're directly calling like a free Python solver to run it also without the Cplex installation.
Cplex is an optimization.
Cplex is an optimization software, yes, basically for the matching part and for this lower level part of the rebalancing policy where we solve an optimization problem. We're using Cplex. And yeah, so then when you run this, you can actually see that the testing starts, and we usually test for several episodes, of course, because we have a stochastic environment and we kind of want to figure out the mean performance of the methods. And if you run it, you will also provide with those two plots where we basically compare. Here on the left, we always compare the performance to the no control policy that I just explained, right? We always want to kind of outperform just having the environment run without any control at all. Where we can obviously see, okay, to no surprise, just doing random rebalancing is actually not better than doing no rebalancing. And here on the right, we kind of try to visualize the policy where we kind of where we show the proportion of the demand in each of the regions and the incoming flows. And ideally, of course, you want to come to align the incoming flows with the demand in each region. And here we can just see in random rebalancing, we are rebalancing into a lot of regions where there is no demand at all. Okay, then coming to kind of a more interesting part, if you want to contribute with your own methods or your own controller to our code base, we actually already provide some, like a base algorithm in one of the files, which just expects this kind of select action function, where in which you can basically implement whatever you want to your policy to do. And then similar as in reinforcement learning or in any controller, the input to this function would be the current state of the environment. Then you implement your controller, and the output is then the final rebalancing action. And in this case, this is actually the implementation of this equal distribution baseline, which kind of aims to just equally distribute the vehicles in the network. And we can see here, this is the kind of important part, is just that the action is the same for each region in the vehicle, in the simulator. And we then transform this kind of desired equal distribution into the low-level flows, similar like in our reinforcement learning agent case, where we take this desired distribution and here solve this lower-level optimization that solves this distribution for the minimum cost flows. But again, in here could be anything, any heuristic, could also be another optimization model. It's just important that we have this select action function and that outputs the action. Yeah, and of course, the equal distribution baseline is also already implemented, so you can test it, but just switching out again this line here where we change the model name from the random distribution to the equal distribution. And then we can in fact observe that we're now finally outperforming the no control baseline. And we're also kind of aligning more our actions, like incoming balancing flows with the distribution of the profit in our environment. Okay. However, this kind of equal distribution, by just setting the action here into equally distributed across the regions, it's of course more a reactive policy, so it can only react if there is a lack of vehicles in one of the regions. But ideally, we want to be a bit more proactive with this. So instead of just setting this into an equal distribution, we can learn this distribution as we've seen in today's talk. And yeah. And in our code base, we already provide all of the pre-trained agents for the scenario. So if you don't want to train them yourself, you can just test them by loading them for all of the environments. And by doing so, we can see that now we are outperforming the no control baseline by a large margin by using reinforcement learning. And we can also see that the rebalancing flows now much more align with the profit distribution in each of the regions. Yeah, so basically what we've seen so far is kind of the comparison of the different like baselines and our RL methods in this repo. We also have some other baselines, of course, implemented that I didn't show like all of them, but you're free to kind of play around with this notebook and just change out the model names and you will see all of the performances. Okay. Then we also have like a quick excursus in how you can actually implement an RL agent yourself, or kind of play around with how you would structure your GNN agents or your neural networks. And generally, as we presented today, our policy would takes a state as an input, then kind of processes this with a neural network and then outputs an action for this state. And yeah, in Python, when we use the PyTorch framework, this is how you would usually implement this type of policy, which here consists first of like a several amount of linear layers, which are basically just linear projections. And yeah, the amount of layers and also the amount of hidden size here is basically just showing the capacity of the actor, and that is usually kind of also very dependent on the project that you're trying to solve with it. And here this is the forward function. That's actually the function that is called when you're calling the actor class here, and it takes in state as an input and outputs an action. And first, when the state is coming as an input, it will be processed through this kind of set of linear layers, as I just explained. And then the output, of course, has to be kind of sampled from some sort of distribution, where here we want to have distribution that adds up to 1, because we want to have distribution that is the desired ideal distribution across the network. And for this, we use the Dirichlet distribution, but this can be any type of distribution that basically fits your problem, of course. A common one, for example, also a Gaussian distribution. And yeah, then you sample the action from your reinforcement learning policy distribution. And that's basically already an implementation of a very valid policy network. Okay, if we then want to use this policy in our scenario, for example, we would have a state that is just like a dummy tensor for now, but we have a state that is, for example, consists of 14 nodes, and in each region we have 13 different features. Since now here we just use this kind of linear layers, they expect a vectorized input, as Daniel presented in his talk. So we need to kind of flatten this matrix into a vector, and then can input this into our actor network and then observe basically our final action, which I here plotted. And basically, if you would run it again and again, you could always see that you get a different sample from our Dirichlet distribution. Yeah. But yeah, as we kind of seen in this tutorial, using graph neural networks instead of MLPs have a lot of desirable characteristics for our transportation applications. So how can we change what we've just seen to kind of include this graph convolutional neural network? And luckily, there's already a lot of packages online that kind of does all the heavy implementations for you, and you can just import different type of graph neural networks from those packages. And the package that we're using is Torch Geometric, which is a quite common one. And basically, you can just already import a pre-done implementation of this graph convolutional neural network. And where you can see here, the only line we kind of have to change is that instead of directly passing our state into the linear layers, we can just pass them first into the graph neural network. That is already pre-implemented. So it's very easy to kind of also implement yourself or switch out the type of graph neural network. It's also just a one-liner if you want to try different ones. And then when you want to run the actual actor, you can see that now our input is a bit different than before, where we just had to flatten all of our state into one large vector and input it like that into the actor, because now actually it expects a graph as an input. where we don't have to flatten our state anymore, so it can stay in this graph format. And then of course we also have to input an adjacency matrix, which we call here edge index. And here it's just a dummy. I just connected basically the neighboring nodes. And yeah, when we then input this, we can basically observe as well how we can have samples from the Dirichlet distribution. And if you keep running this cell, you would always just observe a different sample from this distribution. Okay, then after basically doing all this implementation of your agents, you want to, of course, also train it. And for this, we provide the training script that I showed in the beginning, where first you can kind of just run our pre-implemented actor and critic networks with algorithm of your choice. And you would do this like so, basically just, again, choosing which model, like which algorithm you want to run, on which simulator city and which simulator, and then you would kind of choose a name for the model, and then for how many episodes you would train it, and then just run the training script, and that's it. Of course, in the README, you could see there's a lot of different parameters that you can change, but we already calibrated the parameters from our algorithms that to match the simulator, so you should be fine just using the provided parameters. And then, of course, after you train it, you can test it exactly the same way as all of the other policies before, by just calling the test function again. Okay, yeah, like I said in the beginning, we don't have the Sumo environment in this notebook, as it's a bit annoying to install Sumo in the Google Colab notebook. But of course, by just switching out again this line from the macro environment into the Sumo environment, you're just able to do exactly what I just showed, just for the more mesoscopic Sumo environment. Yeah, here we even have an example on how you could run the MPC on the Sumo environment, for which we currently provide the city of Luxembourg that Luigi just presented in his talk. Yeah, I know that was a long monologue of code, but I guess it really helps, like, if you're interested in contributing, just if you have some time, pulling up this notebook and try to kind of interact with it. And we would be very happy to see some contributions to this. That's the goal, and that's also very encouraged, of course. And yeah, of course, if there's any questions. Yes, sure. Yeah. Yes, totally right. Here I just kind of stripped it down a bit to make it easier to present, but you're totally right. When we do the testing, you would also see this if you open up the actual implementation here, there would be an input parameter to see if we're in testing or not, and then you would take a deterministic action, actually, and not do the sampling. Yeah, the sampling is just for exploration during training. Yeah, that's totally right, yeah. Yes. Yeah, so we take actually historic strip data, like also this kind of, for example, the famous New York City taxi data set, and incorporate this as a demand in our simulator. So basically, yeah, if there's demand, we assume that the people are waiting currently and are also always ready to match. So basically, we would have this matching algorithm that Daniela presented in his talk. And once a person shows up, it will be matched if there's available vehicles. And if not, they will wait for a certain amount of time and then leave the system. Did this answer your question? Yes, yeah. I mean, so basically, if we see in historical data that there would be demand, we kind of just replaying this demand in our simulator, where we assume that, yeah, it's it's a current demand in this time thing. Yeah.
Yeah. I can also define different kind of groups.
Yeah.
And actually, I would say part of this would be created in different environments where kind of as this repository, calibrated scenario, we are providing a bunch, but there could be, yeah.
There are tools which define which is repository, like for example, like staff. You have to do the last time you were doing as this repository,
Yeah, because the SAG and the HOC is just the algorithm how we train the policy network. So that's kind of just vanilla state-of-the-art algorithm. But then the policy design itself is, of course, depending on, of course, what you would use. But the way we currently set it up is from the first talk that we have this kind of hierarchical framework where the output here is this kind of desired distribution, and then it will translate it into the ones. Yeah, but yeah, that's right. And currently, we just set it up that this is the way the policy is called, but the trading algorithm itself is completely independent in how you set your policy and how you design your policy. Yes, so you could also design it in a way that yeah, you have a different type of policy that's network. Yeah.
Are there any like restrictions about using these repos? For example, sometimes some repos are available online, but they are available online under the condition that, for example, for if when you have some contribution, you do make that contribution first, the like public repo. You have those kind of restrictions.
I think it's the standard MIT license. So but not for business, I'm not sure. You double check.
I mean, everything we do at university is owned part of the university. So, you know, create a startup that uses this, probably MIT Stanford or something. Nobody using it for like non-profit. Oh, I think it's a very standard.
Very open.
Nobody needs to be from the level. It's MIT like it's really whatever you want. The elements that need to put up anything there. So don't do it. Yeah.
But yes, I didn't.
Yeah. Thanks very much for coming and to create the network of people interested in. Thank you very much.